All right, so now we are moving on to air masses, fronts, and large scale systems, our sort of second portion of week three's content. And this is another going to be a two-part video. Unfortunately, with how things split up, the it sort of fits into three subsections here. And the middle one's a lot longer than the others. So this first video is going to be a little bit shorter than the second one's going to be. But hopefully it'll all make sense once you watch them all together. So let's get into it. So starting out, the foundational concept for this section are air masses. And air masses, by definition, are large bodies of air that are relatively uniform. They're relatively the same. And how we define that or look at that is with thermal and moisture characteristics, or its temperature and moisture. And of course, if you say large, how large is large? And we generally consider these to be synoptic scale. So going back to last video, those are lengths on the order of 1 to 5,000 kilometers. But just based on how it practically works out, sometimes they don't quite reach synoptic scale. They're on the upper level of mesoscale. So we can't say that they are exclusively synoptic scale phenomena. But if you wanted to get a ballpark idea, you can consider that sort of 1,000 kilometer length scale in size. Also, they're generally surface based. As we'll get into, they tend to form because of the surface characteristics of where these air masses come from. And so, because of how the atmosphere flow works, it tends to just be where there's consistent surface interactions. So they can be very shallow, only like a kilometer in depth, sometimes more than that. But they never really take up a majority of the troposphere. They form over relatively flat regions, so that allows these relatively uniform characteristics to develop because we want homogeneous surface characteristics so that being in contact with the surface, the air can also develop uniform or homogeneous characteristics. Because the air will reach equilibrium with the surface in that source region. That's what makes up an air mass, because it's uniform and it reaches a stable equilibrium of its characteristics. And I say is if it's, still there where its source region is or was. These move around and that becomes important later on. So starting where they come from, again, prolong contact. And it's a days to weeks sort of time scale to allow this to happen so that the air can come into equilibrium with the underlying surface, so it can justifiably be called an air mass, where it's a large body of air with uniform characteristics. And the main source regions sort of have a global map of the most common ones here. And they typically are those where there's permanent or semi-permanent anticyclones or high pressure systems, because that allows for relatively persistent air to stay in around the same region so it can develop these characteristics. And again, as a reminder, these high pressure systems are anticyclones. In the northern hemisphere, they tend to rotate clockwise. In the southern hemisphere, they tend to rotate counterclockwise. And so we also want to actually talk about these air masses or label them. So we have this particular way of categorizing them. Of course, going back to thermal and moisture characteristics, so we categorize them by temperature and moisture. There's a few more temperature categories. We have Arctic at the very coldest and polar as our cold temperature type air masses. And then tropical, the ones that tend to develop in your more tropical latitudes, and equatorial, where it's right around the equator. Practically speaking, we talk about polar and tropical most often, and as you might see from this list below or the map over here, those are the ones that affect the continental US most often. We also talk about the moisture of these air masses. This we just have two categories. Maritime, if it's moist, coming from over the ocean. continental. If it's dry, coming over land. So typical types that affect CONUS, the combinations are continental tropical, so that's warm and dry air mass. Common source region for that is over the southwest of the US. Maritime tropical, that's a warm, moist air mass coming from over here in the Pacific or over here, Gulf of Mexico, Caribbean, more southern portions of the Atlantic, relative to the US, of course. Continental polar, these are the air masses that tend to come down from Canada. We're talking, again, US. And maritime polar. We also get some of these cool, moist air masses coming in as well. And the last one here, Arctic. We typically just say Arctic because those are so cold that they're always dry. And these are the ones that come from either like northern Canada or over the Arctic Circle. So again, air masses are interesting, not just because they are a useful tool for describing large bodies of air, but because they move around. So this movement is driven by interactions on the synoptic scale, typically with upper level flow, talking about the wave patterns from last time. But when these air masses move around, they collide with each other. And the boundaries between those colliding air masses are what we call fronts. Now, fronts are a very key concept in meteorology, and they'll show up a lot as we talk about different phenomena. And just one sort of technical note or conceptual understanding type of thing here is that these boundaries are not sharp walls. They're actually transition zones because in the atmosphere, it's a continuous fluid. We don't have complete drop-offs in variables where it's just a completely sharp transition between two different values. So, but because these zones, you can sort of see here, the zones of transition are so narrow in their width compared to their lengths, it's really useful to talk about them as lines. And it's a pretty good approximation when we're looking at things on the scale of the US. And so for the rest of this video, and probably most of the rest of this course, I'll be talking about fronts as if they were just lines rather than actual zones of transition. So it's a conceptual thing to keep in mind, but again, practically, we'll talk about them as if they were lines. And so we get into actually talking about these kinds of fronts. If we want to categorize fronts, a useful tool is talking about the cold air, because cold air, being more dense than warm air, tends to control the movement of these boundaries, because cold air, or denser air, tends to be the one that if it moves around, it's going to push or force the less dense air out of its way. So the cold air, when we talk about these fronts, controls the boundary position. So we classify the major types of fronts according to the direction that the cold air mass is moving. If we have the cold air moving away from the boundary, that's what we call a warm front. If the cold air isn't really moving at all, that's a stationary front. And if the cold air is moving toward the front, toward the boundary, that's what we call a cold front. And we'll go into all the details of each of these different subtypes, as well as a few other little things like what happens when they collide, what kind of front do we call that combination, as well as this last little bit, these mid-latitude cyclones, talking about our typical large-scale systems that incorporate fronts together with low-pressure systems like we talked about last time. And that's going to be coming up in the next video right after this one. So stay tuned for that.